When you look out at the cosmos, you see all these incredible galaxies, right?
Yeah.
But how did they get there? How did we go from, well, basically smooth stuff after the Big Bang to all this?
It's a fantastic question, and it's exactly what we're diving into today, using this galaxy formation study guide as our reference point.
Okay, so that's our mission.
Yeah.
Unpack how galaxies form and evolve based on this guide. Let's do it.
Sounds good. Maybe start with the absolute basics. What even is a galaxy?
Yeah, good point. What are we talking about here?
Think of a huge, self-contained system in space. It's got stars, loads of them, billions, sometimes trillions, plus gas, dust, and this other major ingredient, dark matter, all held together by gravity.
Like the Milky Way, our galaxy, or Andromeda.
Exactly like those. Those are sort of your classic examples of large galaxies, or these immense structures.
Okay, so galaxies are these giant gravity-bound islands. Where did the raw materials come from? Way back.
Right, you have to go way back to the Big Bang. About, what, 13.8 billion years ago?
The very beginning.
Yeah. So initially, the universe was incredibly hot, dense, and pretty uniform. Mostly hydrogen and helium gas, but not perfectly uniform.
Ah, so tiny differences.
Tiny differences in density. And over millions of years, gravity started pulling the slightly denser regions together. These clumps, these were the seeds. We call them proto-galaxies.
Proto, like early versions. Baby galaxies.
Kind of, yeah. The precursors. And inside these proto-galaxies, things really started heating up.
Because gravity kept pulling gas inwards.
Exactly. More gas means more gravity, pulling in even more gas. Eventually, pockets became so dense and hot that nuclear fusion ignited.
The first stars.
The very first ones. We call them population 32 stars. And they were quite different, massive, super bright, but they lived really short lives.
They were just hydrogen and helium, right? None of the heavier stuff yet.
Precisely. They burned through their fuel incredibly fast and then went supernova, seeding the surrounding gas with the first heavier elements.
Wow, okay, so step by step then.
Yeah.
You have gas clouds.
Yep, those initial protogalactic clouds.
Gravity pulls them tighter, starts making stars.
Lots of stars, often in clusters.
And then these clusters and smaller bits, they merge.
They do. Gravity keeps working on larger scales, pulling these star clusters and smaller structures together. That's how you build up the larger galaxies we see. It's a hierarchical process. Things build up from smaller pieces.
And it's still happening. Galaxies aren't finished.
Oh, definitely not. Galaxy formation and evolution is ongoing. Galaxies keep growing.
Ow.
Two main ways. They merge with other galaxies, sometimes pretty violently, in these huge cosmic collisions.
Right, I've seen simulations of that.
Yeah, they're spectacular. And they also pull in streams of gas from the space around them, which fuels new rounds of star formation. It's a dynamic process.
So that explains why galaxies aren't all the same shape. The guide mentions different types.
That's right. The main types are spirals, ellipticals, and irregulars. It often relates to their formation history and environment.
Okay, break those down for us. Spirals first, like us.
Yep. The Milky Way is a spiral. They have a flat, rotating disk with those characteristic spiral arms. Those are usually sites of active star formation, lots of young blue stars, and usually a central bulge of older stars.
And ellipticals.
Ellipticals are more rounded or oval-shaped, kind of like cosmic footballs. They tend to have less gas and dust, not much new star formation, and are dominated by older, redder stars, often thought to be the result of major mergers.
Okay, and irregulars are just messy.
Pretty much. No defined shape. Often they look chaotic. This can be the result of interactions or mergers that haven't quite settled down yet, or they might just be smaller galaxies without that strong structure.
You mentioned dark matter earlier, the invisible glue. How important is that?
It's absolutely critical. Turns out the stars and gas we see are only a small fraction of a galaxy's total mass.
Yeah.
And most of it is this dark matter.
And we can't see it. How do we know it's there?
Through its gravity. When we look at how fast stars orbit within a galaxy, especially further out, they're moving much faster than they should be if only the visible matter was providing the gravity.
Ah, so there must be extra unseen mass holding things together.
Exactly. That's dark matter. Without it, galaxies would literally fly apart. It forms this kind of vast, invisible scaffolding that the visible galaxy sits within.
Mind-boggling. And our Milky Way just to place us again.
We're in a barred spiral galaxy, hundreds of billions of stars. Our sun is out in one of the spiral arms, maybe 2/3 of the way from the center, just cruising along.
How do we even piece all this together? Studying things that are so incredibly far away and happened so long ago.
It takes a whole toolkit. Powerful telescopes, of course, like Hubble, looking at visible light, but lots of galaxy action is hidden by dust.
So you need other kinds of light.
Right. Radio telescopes, infrared telescopes, they let us peer through the dust to see star formation and gas dynamics. And increasingly, supercomputer simulations are vital.
Running virtual universes.
Essentially, yes, we input the laws of physics, gravity, gas behavior, and watch how structures like galaxies form and evolve over billions of simulated years. It helps us test our theories.
Okay, so key ideas from the guide.
Yeah.
We've got proto-galaxies, the starting seeds,
Yep.
dark matter, the essential invisible stuff,
The scaffolding.
galaxy mergers, a major way they grow. What else? Maybe star formation rate?
Yeah, that's important. How quickly a galaxy is turning its gas into stars tells you a lot about its current state. And maybe redshift.
The stretching of light from distant objects.
Exactly. It tells us how far away things are, and because light takes time to travel, it lets us look back in time and actually see galaxies in the process of forming in the early universe.
So, wrapping it up, it starts with tiny density ripples after the Big Bang. Gravity amplifies them, gas collapses, forms the first stars. These build up into clusters which merge into protogalaxies,
Yeah.
which keep merging and pulling in gas, influenced heavily by dark matter, eventually forming the spirals, ellipticals, and irregulars we see today.
That's a pretty good summary. It's this grand, ongoing cosmic construction project driven primarily by gravity.
It really puts things in perspective. Thinking about all this growth and merging, what does the future hold for our own Milky Way? Is it just going to keep doing its thing?
Well, actually, we're on a collision course. The Andromeda Galaxy, our big neighbor, is heading right for us.
Seriously?
Yep. Billions of years from now, though.
Yeah.
But the current predictions are that the Milky Way and Andromeda will merge, likely forming one giant elliptical galaxy in the distant future.
Wow. So even our galaxy story isn't over. It just keeps changing.
That's the universe for you. Constant change on absolutely epic scales. Makes you think, doesn't it?